Welcome. Thank you. It looks like we're live. So this is the first day of reInvent, and I know you're all worn out from the party last night. I'm going to be fairly quick in my section up front. I really want to set this up for Kobayashi-san from Western Digital, who can drive a little bit deeper into actual customer use cases, specifically around design and engineering in the cloud. So what I want to talk about today is focusing on high-performance computing for design and engineering, things like big simulations that are used in manufacturing and other domains. I want to talk specifically about how these applications are deployed, some of the options for deployment, dig a little bit deep into that topic, how developing a stack for design and engineering, for CAE types of applications, for example, is different on the cloud than on-prem, but also how it's similar. We're going to focus both on compute and on storage, because for many of these workloads in design and engineering, it's not so much their compute bottlenecked, they are often storage bottlenecked as well. So what are some of the best practices there? I'm going to talk briefly about ISV software, about third-party software and methods of deployment of that with some examples as well. I want to talk very briefly about graphics, because it's not enough just to run big compute for some of these workloads. It's important also that you're able to do pre- and post-processing visualizations, remote desktop, streaming types of visualizations for the results, for example, of a big simulation. And again, we're really going to focus on the voice of the customer here today, on the experience of Western Digital in how they've been migrating these workloads to cloud, some of the reasons to do that. So first, let's talk about the motivations for cloud. Why even think about cloud for design and engineering? And it really comes down to getting access to scale, right? Dramatically more flexibility if you can get access to scale when you need it. And of course, that's the general story of cloud. But for design and engineering, which is increasingly dominated by large-scale compute for large-scale simulations, that access to massive scale can be incredibly impactful, right? So you can run cost-effectively on the cloud, and that's really not the primary motivator, though. The primary motivator is faster time to results, higher quality products, getting simulations run quickly, reducing risk, right? So how does this help, right? So the first thing you can do is think about right-sizing your clusters, right? So if you think about simulation, for example, that's used in automotive or aerospace, the idea that you can now create perhaps even 10 times the number of CPU cores, 10 times the amount of storage that you had previously for a shorter burst of time to run these big simulations, to run these workloads, that's incredibly impactful in the design and engineering space. Another reason to think about this that's often not thought about is the idea that you can create secure chambers for design, right? So let's think about the situation where you're globally distributed and you've got contractors or third-party collaborators, maybe providing intellectual property or design consulting and so forth, and you can carve out and create secure chambers to collaborate. It's very difficult to do that in a physical data center. It's quite easy to do that in the cloud. Another reason to think about that is when you're working with an ISV partner, and maybe there's some issue that you found with their software. And historically, it's been very difficult to give your software provider access, right, to your IT resources to duplicate that problem at scale. It's relatively easy to do that in the cloud. And then on-demand workstations, that's super important. So don't just think about cloud as a place to run great big simulations, to run lots and lots of compute in a batch mode, but really think about cloud as the place to deploy the entire workflow, right, including interactive desktops, right? And as you move to the cloud, there's another motivating factor, and that's the increased use of big data technologies, data lake, machine learning, deep learning. And these are some things that Kobayashi-san will talk about later that Western Digital in particular is using at scale, in addition to HPC, high-performance computing. So here are some examples of workloads that we're seeing now running in production on AWS. And many of these workloads historically would have demanded specialized compute infrastructure, high-performance computing infrastructure, but increasingly, these workloads are moving aggressively to cloud for the reasons I mentioned before. And you do have access to the high-performance resources that you need. high-performance CPU-based instances, now GPU instances, higher performance networks and storage. You have many, many more options today than you did perhaps in the past when thinking about deploying these types of applications on cloud. Now, some of these applications I listed here are definitely HPC-centric, high-performance computing, right? These are things like fluid dynamic simulations and magnetic simulations. But a lot of them also are big data problems. They're machine learning problems in areas like logistics, for example, yield analysis. So let's dive deep and let's talk more about how you optimize performance of these applications and how you deploy these applications. If you look at a traditional data center or deployment perhaps in your office for running CAE workloads or computer-aided design workloads or even electronic design automation workloads, the pattern has evolved over literally decades, and it looks much like this. You've got, sort of in the middle of this, you've got HPC clusters. So maybe in the back room of your office, you've got a rack of servers, or maybe if you're running at scale, you've got a data center that's just chock full of high-end servers. You're constantly having to refresh those, right? And then you're going to use those in a kind of a batch mode using job queuing software, things like LSF and SunGrid Engine, and there's other options as well, to manage the batch jobs against that cluster. So you're going to need some head nodes. You probably have licensed software that you're using from various EDA or CAE vendors. And you need to run license servers, typically Flexera license servers, right? Many of the workloads, as I mentioned before, are storage intensive. So it's often the case that the compute cluster is matched by a perhaps equally large and expensive storage cluster. And these are storage clusters by well-known vendors of NFS types of solutions. And that is typically the dominant storage in a CAE environment, whether it's automotive or aerospace or semiconductor. Very expensive high-performance shared storage sitting next to very high-performance and expensive CPU clusters that are running 24/7 job queues, just throwing jobs at those all the time. The problem, of course, with that is it's not scalable. Can't scale up and down when you need it. It's very expensive to maintain, and you really have to be able to plan pretty far in advance to deploy and use those types of systems. And then finally, at the top of the stack, increasingly, remote desktop is part of the picture. So rather than putting a high-performance graphics workstation on every engineer's desk, push that out as well to the data center with remote desktop technologies, right? So when you think about migrating this sort of thing to the cloud, the first thing you want to think about is how to minimize disruption, how to minimize change. And you can really duplicate that same environment on AWS, in a virtual private cloud, in a VPC. The primary difference when you do that is that now you can create, through automation, the ability for that cluster to grow and shrink, right? That's super important. And we have methods I'll describe a bit later that can help to automate this and get it started that would, for example, monitor the job queue of LSF or SunGrid Engine or some of these other tools, and as more jobs are thrown on the queue, would automatically scale those up and scale them down. And that's the first thing to think about when you optimize for cloud. But you shouldn't stop there. There's many more optimizations that you can consider. On the storage side, I'll talk a bit about storage later. One of the most important things to think about in storage is taking advantage of different types of storage that are available in the cloud for both cost and performance reasons. Use as much as you can S3 object storage rather than throwing everything onto a big shared file system, right? Use the shared file system when you need it, but don't use it as your primary form of storage. And then on the remote desktop side, you really do have the same capabilities that you had in the physical data center. You can deploy remote desktop protocols using existing tools that you're familiar with, or tools like RDCV, or perhaps AppStream 2.0 for a thin client type of experience with the applications, but there's lots of application options there. Let me talk briefly about license servers, because that's a very common question in this community. How do I manage license servers? So in this environment, because we are hybrid, we're direct connected from the AWS VPC out to a physical data center where we still have some legacy IT, we have a choice. We can either deploy our license servers on-premise and serve the licenses out to the cloud over either a VPN or a direct connect, or we could do the inverse. We could deploy the license server on the cloud and serve licenses into the cloud-based applications and perhaps out on-premise. And we see both patterns, right? Use the cloud for the license server hosting, push the licenses out on-premise, or the inverse. Both work just great. Let's talk briefly about EC2. So EC2, generation after generation, we continue to increase the performance of EC2 instances, deploying the latest Intel architectures, the latest NVIDIA GPU architectures, and now the FPGAs with the Xilinx UltraScale FPGA instances. So you've got a lot of choices when deploying technical software, right? CAE software, EDA software on AWS. Our recommendation for most applications is that you start with the C family, either C4, which is Haswell-based, or C5 now, which is Skylake-based. If you need more RAM, then move into the R4s or perhaps even the X1. And we're finding excellent success in some of the most compute-intensive applications, like fluid dynamics simulations, for example, structural simulations, running either the C family or, if you need higher memory, in the R family or X family. And we continue to innovate and add new higher performance instance types over time. The important thing to take away here is you've got a lot of choices, and you should never just finalize your decision on an application and keep it set in stone for years, right? Continually re-optimize and retest with the latest generation EC2 instance, in particular for these compute-intensive solvers that you find in fluid dynamics and structures and so forth, many other applications like that. If you do have the ability to accelerate, we have now, with the P2 and the P3, the ability to deploy applications that are accelerated in GPU, the NVIDIA K80 in the case of P2, and the NVIDIA V100 Volta in the case of P3. So discuss this with your ISV partner, with your software supplier. If they have GPU acceleration available, take advantage of that on AWS. Now let's talk about how you can optimize the workflow, right? In many environments today, IT is a constraint. The number of CPUs you have is a constraint to how fast you can get throughput of a particular set of simulations, for example, right? When we think about cluster computing, when we think about high-performance computing, for example, in fluid dynamics, that's the pattern on the left, where it's tightly coupled. You've got a job that requires a lot of communication between nodes. If you're familiar with fluid dynamics, it involves a mesh. That mesh has a particular density per core that you try to optimize for, but you have to scale it up across multiple cores to get that simulation to run. And simulation depends on having high-performance communication between those nodes. And that's where things like placement groups come in, right? Enhanced networking, taking advantage of our latest generation network performance to get individual jobs to run as fast as possible. Well, next thing you want to do is think about how to run not just one individual job, but how about running many, many parallel jobs, right? Parameter sweeps, for example, parametric studies, running lots and lots of different scenarios. And that's more of a grid computing approach, because the different jobs don't actually need to communicate between each other. So I like to call this a grid of clusters method, right? And this is important on AWS. If you're trying to get scale, if you're trying to run, let's say, 100 CFD jobs that each require 1,000 cores, well, that's a lot of cores. You don't want to try to launch all of that in one placement group, in one availability zone with one instance type, because you can actually run into capacity constraints because you're trying to put everything in a placement group. The better strategy is a grid strategy where you launch individual jobs, let's say 1,000 cores each, in different placement groups, perhaps even in different availability zones, right, to spread that load. And that will give you much higher success in getting the capacity you need when you need it, in particular if you're using something like spot instances to cost optimize. Grids of clusters, it's an important concept, right? But if you use that concept, now you can start to think about ridiculous levels of scaling. Many, many jobs running in parallel that previously in an on-premise cluster would have been run in sequence using job queues. And that allows you to think about massive levels of design exploration, right? So run many, many more studies than you did previously. Now, you may be constrained, of course, by software licenses from your vendor, but if you're not, if you're using open source software, or perhaps your ISV is providing you with the ability to scale up dramatically in their license terms, you can do some pretty incredible parallel studies of these types of applications using this method. One example of this is customer TLG Aerospace, and they're a consulting firm up in Seattle. They work with a lot of aerospace companies, and they do fluid dynamics and structural simulations for the aerospace industry. And what they've talked about, and this is a case study, it's available by the way, is reducing the time to go from that design and configuration part of the process to actual flight testing. And the shorter you can make that, that duration from design to flight testing, obviously the faster you can get something that will fly and meet the customer objectives, get higher quality. And you don't want that thing that you put in the air to not fly well. That would be a bad thing. So that requires a tremendous number of simulations, right? Parametric studies, right? And so that's what they do. They launch on AWS. They'll launch individual jobs of, let's say, 1,000 cores. They'll run many of those in parallel. They'll iterate fast. They'll use spot instances to save money. And they get this work done much, much faster. Another example, Richard Childress Racing. So this is a NASCAR team, RCR. And they do the same thing, working with our partner Rescale in this case, who provides them with scalability and provides them with a managed service for running Star CCM, which is a solver that's commonly used in the aerospace and automotive industry for fluid dynamics. Same thing, right? So going from their previous relatively small on-premise cluster of 64 cores to moving to 512 and more on AWS, and allowing them the ability to run many, many of these studies in parallel has dramatically increased the speed at which they can get real-time data for the car design. And this is very impactful in car racing. Let's flip and talk about storage now. Storage is very, very important in many of these applications. I work a lot, for example, with semiconductor customers, and storage is just key there. They're hammering shared file systems to get these regressions run in the semiconductor world. And you see it also in media and entertainment rendering. You see it in other industries like automotive and aerospace, where there's a lot of data that has to be pulled in these simulations. So you've got a lot of options on AWS. If you're familiar with running shared file systems, NFS file systems, you have two options depending on the performance characteristics that you're looking for. Starting from the left, you have access to EFS, Elastic File System. This is a fully managed shared file system deployed on AWS. It's built for scalability, for durability. It automatically scales up and scales down. You only pay for the data that you're storing. Super easy to use. And from a throughput perspective, very good performance, right? So this would be an excellent place to put libraries, to put applications, to put things that are needed in the course of the run that haven't yet been architected away from using shared file systems. If you need extremely high IOPS, right, you're hammering that file system, very small reads and writes to lots and lots, millions of files over the course of a run. Now you might consider building a customized file system on AWS using a combination of EC2 instances, our latest generation, higher performance EC2 instances, in combination with EBS. And with EBS, of course, you have the choice of provision IOPS or general purpose. In most cases, general purpose serves very, very well for shared file systems. What you really need to have there to create a high-performance shared file system is a high-performance filer that's deployed on a high-performance EC2 instance. There's lots of options here. You can handcraft something yourself. You could simply create maybe an i3 instance and use that as your storage node. Or you can use one of the file systems mentioned here from one of our partners, right? Weka.io, Avere, NetApp has a solution here. There's actually a lot of solutions for shared file systems on AWS, and that's a great approach if you need that extremely high IOPS solution. And as I said before, never stop, re-optimizing your file system, because we're continuing to innovate in this space. Our partners are innovating. The EC2 instances that are available to you continue to change. So continue to reevaluate and retune your shared file systems over time. But to the greatest extent possible, reconsider shared file systems as they are typically used today in the CAE, EDA, simulation world. As I said earlier, a common practice today in the legacy IT world supporting these is to put everything on a very expensive, difficult to scale, shared file system solution. And that's not really the best alternative on AWS. The best thing to do is begin to re-architect your workloads to take advantage of object store when you can. That should be your source of truth, if you will. Life cycling data out to Glacier that hasn't been touched, pulling data when it's needed into a high-performance shared file system, for example, to run a very large regression test or some large set of simulation studies. Pull data from S3, populate a shared file system, run the applications, push back to S3. That's a much more effective pattern if you can do it. So optimize that storage data flow. And again, there's so many options for data ingress for shared file systems, using local storage on an instance versus creating a shared file system. But the best way to think of it is that the primary storage medium for any application, and certainly in the engineering world, should be object storage, should be S3. That's where you should push data when it comes in from your, maybe from your on-premise data center. It should be where the data lives long-term, so life cycling out to Glacier. And when you need high-performance shared file systems, create them, populate them, use them, tear them down, right? Also think about pricing models, right? So when you optimize on AWS, you have a lot of choices for pricing models, and we continue to innovate in that area as well. But if you're not using Spot for these types of applications, you're really missing quite a big opportunity to optimize. And the best way to think about this is to create a blend. You may have need for some applications that just run steady state for a long time. Spot termination would be problematic, perhaps. Or perhaps you just need to have the reservation, a capacity reservation, so that you know it's there. So you may have some base waterline, if you will, of reserved instances that you deploy in your account. And on top of that, you should be using Spot as much as possible to run your simulations. And only for those cases where you can't get access to Spot, or you don't have reserved instances and you need to run some job in a much more dependable way over time that can't be terminated, then dip into on-demand, right? So the area under the curve might be the effective utilization of these different pricing models. Spot should be a very important part of your thinking for these types of applications. I'm going to talk very briefly about graphics and deployment, and then turn it over to Kobayashi-san to talk about their experiences. I do want to emphasize that we have many different options now for graphics on AWS. Different instance types. We've got elastic GPUs. We've got partners and our own services for remote desktop. So you have a lot of options to choose from. Your ISV partners may also have some particular needs around graphics and some solutions that they've settled on. So no solution that I expressed today is really going to be perfect for anyone. But it's enough to know that graphics is supported very, very well on AWS. And for engineering types of applications, for example, collaborating on a 3D model that was a result of a simulation is very effective. And it's far more effective than pulling data back down and using it on premise, perhaps in a local desktop, and then pushing it back up to do another simulation. It's far more efficient to push pixels to your face and mouse clicks out to the cloud than it is to try to move data back and forth all the time. So DCV is an enabling technology that we have. That was an acquisition that we made of Nice Software. A DCV protocol allows us to do things like create the elastic GPU service that we've talked about previously, and to enable remote desktop capabilities. It's a very, very powerful capability that we have. DCV, desktop cloud virtualization, is a remote desktop tool and protocol that's available from AWS. And this supports engineering types of workloads. It was really built for engineering types of workloads. Related to DCV is the elastic GPU capability, right? Elastic GPU allows you to create GPU acceleration, in particular intercepting and accelerating graphics calls for instances that otherwise would not be graphics enabled, right? So for example, if you need to run maybe a C5 instance that I described earlier as being great for simulations, and on that same instance you want to log in and actually interact with your simulation, use graphical tools, then Elastic GPU allows you to connect, if you will, a GPU to your C5 instance. It will intercept the graphics calls, accelerate those, so you get an accelerated environment for your visualizations. AppStream 2.0, somewhat related to DCV and Elastic GPU, AppStream 2.0 is not a desktop service per se. It's more of an application streaming service. What I mean by that is AppStream 2.0 allows you to create a thin client experience. So for example, if you're an IT manager that's supporting engineering teams in your organization, you might want to give those engineering teams secure and reliable access to a subset of applications that you have qualified them to run. You don't want to give them an entire desktop and file systems and operating systems and all of that. You just want to expose the applications. And that's what AppStream 2.0 allows. It allows you to secure the applications. It allows the applications to interoperate, right? Sharing files, for example, between them. But it doesn't give the end user access to that full desktop and that full operating system. So it's a great alternative to providing fully managed remote desktops. It's more like fully managed applications in the cloud. And it supports a number of different graphics levels, graphics capabilities based on the elastic GPUs that we have available. Supports a number of different protocols. We work with ISV partners to qualify them, to get them up and running. But in most cases, an application can be deployed on AppStream 2.0 without any change. So it provides a very simple user interface, a browser-based user interface, thin client experience for customers that are trying to do technical and graphical applications on AWS. So again, that was a very quick tour of graphics. There's so much more to learn, and there are sessions through the week regarding graphics capabilities. Let's talk about software, though. Software is incredibly important in enterprise engineering applications. And I'm talking about technical software vendors, folks like ANSYS and Dassault and Siemens and Synopsys and Cadence, right? And these are ISVs that are critical to the success in many industries of engineering projects, right? So there's a number of ways that you can deploy commercial software on AWS. And starting from the left, ISV managed. That's often referred to as software as a service, but there's actually many different ways to think about vendor managed software, right? So that would be the experience where your software vendor provides you with a login portal, right, where you can go to a site. You don't know or care where it's running. You do care that it's running in a secure manner, so you want your ISV to be well deployed. But the ISV is managing the deployment of that software, the compute infrastructure that it runs on, and you pay them, perhaps pay per use, of that software. Maybe it's probably running in the cloud, right? And that's something that could be delivered via AWS Marketplace. It could be delivered via the ISV's website. There's many different experiences that you could have running like that. For technical software used in areas like automotive manufacturing, semiconductor, aerospace, energy, that's not typically the way customers are using software, in particular technical software. So the next one over, supported, this is where you are going to control your own destiny, if you will. You're going to run in your own data center or your own virtual private cloud on AWS, and you're going to deploy the ISV's software in your account. So you manage security, you manage the serving of licenses, you manage the workflows, right? And that is more similar to what you've been doing in the on-premise world previously. Supported, though, means that the ISV partner has endorsed this, supports the use of cloud, supports maybe a particular type of deployment, right? Different instance types, for example, that they've qualified on, different ways of managing storage and security, and they're with you, right? They're supporting you in this. And that's where most ISVs are today and most ISVs are going. Self-managed, the next one over, that's where you have perhaps not asked permission of the ISV to run it on the cloud. You just did it, right? You just, because you've got the VPC, you've got the direct connect, you've got the license server set up, you just run it, right? And that's fine. That's many customers do that. There may or may not be license terms that you need to consider about location of the deployment servers and so forth. It is important that you have a conversation with your ISV to make sure that if you are self-managed with a piece of expensive technical software, that you're actually operating within the terms of the license agreement. So we do recommend you have that conversation when you deploy on the cloud. And hybrid to the right, that's where you mix all of these together, and that's very common now in enterprise software. You've got some applications that are running software as a service, some applications that are ISV managed as sort of a managed service provider experience. Some of them you're self-deploying, maybe they're legacy software tools. Some of them you're still running on-premise and connecting out to the cloud. So in reality, most engineering organizations today that are migrating to cloud, including Western Digital, is in this hybrid mode where they have to manage multiple types of software deployments. A great example of an ISV that's been quite progressive around this is Cadence Design Systems, who supports the semiconductor and electronics industry with a variety of solutions. And what's interesting about the Cadence approach is they've seen that both are needed. You need to have ISV managed solutions for some categories of customers and supported cloud deployments for other types of customers. So on the left, customer managed would be the case where they have the customer is running in their own virtual private cloud on AWS, wants to stand up a license server, wants to operate that software, and Cadence is providing a support for that environment using something they call Cloud Ready with a passport, right? And that passport might include alternative licensing models as well. On the right, the Hosted Design Solutions Cloud, that's the more fully managed, ISV managed software as a service type of environment, right? So you have choices with a vendor such as Cadence, whether you do self-managed but supported by the ISV or fully managed by the ISV, right? Important that you have choices. So again, they endorse the use of AWS for their customers using this passport model, and they provide this hosted design solutions, right? And if you're interested, I think there are probably some folks from Cadence here who would be happy to chat about this model. I really wanted to turn this over to Kobayashi-san of Western Digital. And Western Digital has been on this journey now for probably 3+ years, moving workloads to cloud, both in big data and in high-performance computing for engineering simulations. Western Digital is also unique and interesting because they've been growing by acquisition and having to integrate many different teams that have different legacy IT. So I'll turn it over to Kobayashi-san, our friend and collaborator in this journey to cloud at Western Digital.
Okay.
Thank you.
Thank you. Thank you, Dave. Hi, everyone. I'm Hiroshi Kobayashi. I'm from Western Digital. Today, I want to introduce a little bit about how Western Digital is using AWS for high-performance computing. By the way, are you enjoying re:Invent? How many people? Oh, that's great. How many people joined the last night party? Oh, very few. Unfortunately, I could not attend that party. Anyway, super exciting week has just started. I'm super excited too, and I'm super honored to be here. I will cover several things, introduce Western Digital, actual use cases, and the next step of Western Digital Cloud HPC. Again, my name is Hiroshi Kobayashi. I'm working at the Western Digital for Global IT Infrastructure team. I'm based in Japan. 10 years ago, I was a mechanical engineer. I loved CA simulations. I did CA simulation by myself. After that, I moved to IT team, and I'm working as admin for HPC clusters and AWS. Of course, I still love CA simulation. My favorite services, AWS services, is AWS CLI and AWS Patch. I think in this room, there are a lot of HPC guys. HPC guys love command line tools with black background, I think. Am I correct? And some of you may know Japanese AWS users are very active in their community. The Japan AWS user group is called JAWS UG, having cool shark icon. I'm chairing one of the user group about HPC with my friend. Let me introduce Western Digital. At Western Digital, we develop, manufacture, and sell not only hard disk drive, but also solid-state drives, flash memory, and storage-related systems. We have over 30,000 active patents. Our global footprints span North, South America, Asia Pacific, and Europe. Until recently, Western Digital was a traditional hard disk drive manufacturing company. But in the several years, we have been very active about company acquisition. Last year, we acquired SanDisk. As all you probably know, SanDisk is one of the leading companies of solid-state drive and flash memory. So Western Digital has a very broad product portfolio now. We no longer just a traditional hard disk drive company. Western Digital is a comprehensive storage solution company now. Our product portfolio covers 3 pillars: client solution, client devices, and data center devices and solutions. We sell everything about the storage: USB flash memory, SD card, hard drives, object storage, flash storage appliance. You name it, and if it's storage, we probably have it. This broad product portfolio was made possible by integration of 3 companies: Western Digital, HGST, and SanDisk. Each company was a Fortune 500 company. Let me tell you, it's a really big and complicated company integration. Not the type of things you got to experience every day. In this integration, AWS Cloud plays a big role by making Agile ID infrastructure integration possible. So AWS Cloud is an enabler for us. So now I will cover the background materials. Let me move on to the actual use case. First of all, let me show overall architecture. We have dedicated AWS account for HPC. We use Direct Connect for primary network access. We spin up clusters based on usage. Some clusters are shared within a team. Other clusters dedicated for applications or users. For cluster management, we use Cycle Cloud provided by Cycle Computing. In the HPC VPC, there are several cluster master nodes where the user access to. Users submit the jobs on the master node with qsub command, and the cycle cloud will process the requested resource information like a CPU core, GPU card number, amount of memory, etc. Cycle cloud will spin up the computing instances based on the requested information. Cycle cloud main task is handling the automation. For the cluster shared storage, I use i3 instance store for higher I/O. i3 instance have NVMe SSD. It have really fast I/O. I like i3 instance very much. For computing node, we choose from compute optimized, memory optimized, or GPU instance based on the requirement of application and its workload. Again, for optimal performance. So let's see some of actual use case. First one is hyperscale CPU cluster. This is probably what would be considered as a stereotype use case for cloud HPC. We have both commercial and in-house application for design simulation. As I said in previous page, we have auto-scale computing cluster. Users submit a job on the elastic CPU computing cluster, and sometimes it may have hundreds core, sometimes 1,000 core or more. That elasticity allows the user to verify all of the possible design patterns. Now, we utilize spot instance as much as possible, especially in such a big cluster. For example, we had run 80,000 core with only $5,600. That shortened 30 days computing into 9 hours. First result with lower cost. That's a big reason why Western Digital use AWS for high-performance computing. Next one is GPU. We use GPU cluster for both HPC, high-performance computing, and deep learning. In the HPC area, we have a code that runs on GPU, and that code is for hard disk drives magnetization simulation. That code runs 100 times faster than CPU. And we also confirm the code on latest P3 instance runs 3 or 5 times faster than previous P2 instance. We always confirm the computing performance when switching the instance type like this. We always confirm the total cost of ownership by analyzing the computing performance against the cost. For the deep learning area, we have a big data analytics platform on AWS, and we also have a petabyte class data lake. To utilize that, we have deployed a deep learning inference server on the top of the data lake. The inference on P2 instance is 25 times faster than GPU. Oh. Let me give you one question though. How many people using a GPU for high-performance computing or deep learning workload? Please raise your hand. Not so many. Not so many. But I'd like to say, I want more GPU on AWS. I hope you want too. So I want to request more GPU capability to AWS. Anyway, let me go back to my presentation. The last one is Docker HPC. We use Docker on HPC cluster. Let the user perform massive parametric survey of SSD system simulation. The simulation code is Python-based. The user only had 32 core computing infrastructure in the past. but they wanted to run 50,000 simultaneous jobs. So we ran a proof of concept project. Each job will finish within 10 minutes. And there are no communication between the Docker containers. Each Docker container runs single independent job. Spot instances is perfect for this kind of job. When I first get this request, I consider using Lambda. Lambda is one of the competing instance. User just required developed application. AWS will handle or manage all of infrastructure portion. But the Lambda has a 5-minute execution time limitation. But the user task will up to 10 minutes long. So I had to give up Lambda. At first, we deployed the Docker cluster with NFS shared storage. But the user started hitting a few thousand simultaneous jobs. The Docker cluster stopped scaling due to the massive I/O to NFS. So the user modified the code to store the result file into S3. As you know, the S3 is very good at handling those kind of massive parallel I/O. So by using S3, we are able to resolve the scalability issue on this Docker cluster. Again, let me give you one more question. How many people using Docker for HPC workload? Oh, very few. Interesting. I love to hear these kind of things. So far, I have shown 3 types of computing for design simulation. From here, I'd like to talk a kind of lessons now from my 4 years experience. For me, most important things is shape the computer too much work to be done. Not all the workloads are the same. Problems to be resolved by computing simulation are very complicated. Many involve multi-physics problem. Each model have individual workload, and required computing resource easily changed for the change of the product roadmap, change of economic situation. We got some quality issues in the existing product. Those variables and the permutation are endless. But AWS allow us to shape our computers. AWS allow us to perform fairness, trial and error. So we can evaluate and optimize cloud HPC cluster to all individual workload. Shaping computer, this is not something you do once and forget. It is something we constantly do for better support our customers' needs. AWS continue to improve and innovate their service. We need to track and utilize it to leverage the benefit for our own business. For example, recently, latest compute-optimized instance, C5, was released just three weeks ago. I'm testing C5 instance right now. C5 has a higher clock frequency than the previous instance. We can get 3.5 gigahertz in boost mode. For HPC, CAE, and EDA, higher clock CPU is always better. Additionally, C5 has nice balance in performance and cost. So user can get the computing result faster with lower cost with C5 instance. I'd like to bring this kind of benefit to my company's researchers and engineers as soon as possible. But of course, I cannot do all of these things by myself. To shaping computer and continue to deliver the benefit, we need right tool, right partner, and right team. For example, with CycleCloud for cluster management, and I check the cluster cost almost every day on Cloudability. Cloudability is very useful tool for cost monitoring. When something happened on AWS, I check API log on Splunk. I use Ansible to configure EC2 instances. And I love Ganglia for resource monitoring. I'm sure I'm not alone in this room, right? And Western Digital use Ansys application on AWS. Ansys is very open to cloud. They are providing a cloud license called Elastic Licensing. Recently, I have been thinking this. In the cloud HPC world, we need to behave as a DevOps team. I have been running POC project, benchmarking performance, deploying the cluster, monitoring resources, planning the next step. I have been doing this for last 4 years, and I will continue it. I think this is really like DevOps operation model. So I'm thinking I'd like to sophisticate this operation model more for Western Digital researchers and engineers for delivering the cloud HPC benefit continuously. This is my last slide. Let me talk a little bit about my next challenge. First one is EDA. Basically, EDA simulator require single or few cores for each job. We can base the EDA computing on hyperscale CPU cluster or F1 instance cluster. AWS is providing F1 instance, which have Xilinx FPGA hardware. But I'm not familiar. I cannot code FPGA, so I'm looking forward to see good FPGA machine image on AWS Marketplace. For EDA, license is one of the biggest hurdle. I hope each EDA vendor can provide a kind of cloud license like Ansys or StarSystem Plus, as we can base the computing on cloud. Next one is AWS Patch. I really love this service. We can set up Docker cluster by executing a few simple commands. And we don't need to configure the manage bunch of EC2 instances anymore. So I'm thinking I'd like to expand the AWS Patch usage in Western Digital. Last one is AI and machine learning. Western Digital has a big data platform on AWS. We have a petabyte class data lake. And to utilize it, we have been running several projects about machine learning and deep learning. That's all I have. Thank you.
Thank you. Thank you, Kobayashi-san. So I really enjoy working with Kobayashi-san and the Western Digital team because they've been incredibly innovative. And what they're doing in Japan, in particular with this JAWS HPC user group, is helping to help other customers understand best practices for running exactly these same workloads. It's been very, very encouraging to see. There are some events that I thought I'd point out. I know that we have a happy hour for design and engineering. I believe that's tomorrow evening, Wednesday. If you're interested in that, reach out to me. We'll need to sign you up for that, but we'd be happy to have you. You can meet with some of your peers and discuss deployment of design and engineering on AWS. And also Cadence, who may be here today, they're also having a happy hour Thursday night. If you're interested in what they're doing on AWS and their customers, please join. So I really enjoyed this session today. Thank you for being here today on a Monday. If you have additional questions, we'll be around here for the next few minutes. Thank you again for your time today.